Hi everybody, welcome to another video in Calculus 3, section 17.6, surface integrals. Before we go to surface integral, first we learn how to parameterize a surface. So a surface is a two-dimensional object in three-dimensional space. So which means regardless on what space it is in, a surface is two-dimensional object. So that means we're going to need two parameters. So parameterize the surface. You can write parameterize or parameterize. We need two parameters. Right. So two parameters. Now we have R3. So we have three variables x, y, and z will depend on the two parameters that we set equal to. Right. So here's one way to do this. Let's look at this example. Parameterize the plane x plus 2y plus z equal to 4, where x and y is in the units where x between -1 and 1 and y is between -1 and 1. So certainly we have the domain for x and y. So from this equation, we can solve for z. So it's 4 minus x minus 2y, and that is z. So if we need two parameters, we can say we parameterize the surface as follows. Of course, you can just keep x and y if you want to, because here we have the limits for x and y. So yeah, that's the perfect way to just keep x and y. So we have R function of x and y, where we have three. X is x, y is y, and z is 4 minus x minus 2y. Of course, we write this as a vector. So we use a triangular bracket. So just like that. To use angular bracket, right? And then, just like any parameters, we have to specify the limit for x and the limit for y. Of course, if you want to do something other than x and y, we can just use, say, u and v, where u is x, v is y, and u is between -1 and 1. So it's v. Right. So simple enough. As long as we write three variable x, y, z depends on only two parameters. That means we parameterize a surface. Next, parameterize a cylinder x squared plus y squared equal to a squared and z between 0 and h. When we see this, we know for sure this is one of the parameters. So let's say v is equal to z, and we know for sure v is between 0 and h. Yeah. So when we see that, that is one parameter. We just need the other one. Right. What is the other one? For the other parameters, we have x squared plus y squared equal to a squared. A is a constant and h is constant. I should specify that. So both a and h are constant. So in that case, x squared plus y equal to a squared, meaning that we're talking about a circle. We're not talking about disk. That means we only talk about the parameters of a circle. So in that case, we should let x equal to a cosine. We could use theta if we want to. We could do t, u, or v, doesn't matter. Let's use t and y, a sine t. And this is a circle, so t is between 0 and 2 pi. So we have three components there. The components depends on just t and z, or z and t, doesn't matter. Let's say t and z, or t and v. Just the parameters. The name for parameter doesn't matter. We can choose anything. Alright. X can be a cosine t, y a sine t, and v is equal to z is equal to v. So we have two parameters, t and v, will give us three variables, x, y, and z. So in that case, we can say t 0 and 2 pi, and v between 0 and h. Yeah. So we write three variables, x, y, z, in terms of two parameters. Could be anything. Or we can just write in parametric equation. Cosine t, a sine t, and v is equal to, and z is equal to v. Yeah, or we can just use z here instead of v. That's perfectly fine, as long as we have two parameters or two variables. Give us x, y, z, that is fine. So notice that this part is on the surface of a cylinder. Next, we parameterize the surface of the cone, z equal to x squared plus y squared, where x and y inside the disk. Now first of all, we see that this is a disk. Unlike here, a circle. A circle is only the parameters, the boundary, the disk including the boundary and everything inside. So because of that, we will have x is r cosine theta, y equal to r sine theta. Because this is a two-dimensional object, so we need two parameters for that, the radius and the angle, right? So r, this is the disk, radius 5, so between 0 and square root of 5, and theta, the angle theta between 0 and 2 pi, standard for 1 revolution. Right. And when we have this, the equation z equal to x squared plus y squared. But this, by the way, this is not a cone. The surface, this is a paraboloid. Z equal to x squared plus y squared. If we have z squared, then it is a cone. Right. And when z equal to x squared plus y squared, it will be x squared plus y squared, which is r cosine squared, r sine theta squared, and sine squared plus cosine squared is 1. So we just have r squared cosine squared plus sine squared equal to r squared. Bottom line is we have the parameterized r. If you want to use r, you might want to use something else, because this is the bold-face r. Actually, I distinguish that. So we can use this regular r and theta. So we have r cosine theta, r sine theta for y, and z equal to r squared. and r between 0 and 2 pi, and that is theta, sorry. Theta between 0 and 2 pi, and r between 0 and square root of 5. Now parameterize the surface of the sphere x squared plus y squared plus z squared. Usually, if it is a sphere, it would be nice if we use spherical coordinates. The problem here is that we talk about the surface of the sphere, the boundary of the sphere. We're not talking about the interior. That would be a bone, right? A bone is the interior and the boundary. But this time we're only talking about interior, the boundary of the sphere. So, besides, we only need two parameters, right? So, we call in spherical coordinates. We have x equal to r cosine, but r is rho sine phi cosine theta, y rho sine phi sine theta, or sine phi, sorry, and z rho cosine phi. Right. Now this one, the radius is equal to 9. Square root of 9, which is 3. So this will be 3. We're not talking about the interior, right? Besides, we can only have two parameters. In this case will be phi and theta. So 3 sine cosine, 3 sine, and 3 cosine. Phi standard is between 0 and pi, from the north pole to the south pole, and theta 0 to 2 pi. Right. So that's how we parameterize the surface. Just like when we do the line integral, the first thing is to parameterize the curve. Now we just need to parameterize the surface. So there's something similar thing there. Right. Now before we actually go to the surface integral, just want to recall real quick. There are two versions of line integral. So they have two versions of the line integral. This one, of course, is the function. So this is the scalar version of it. And this is the vector version of the line integral. Now, if it is the scalar version, it is representing a mass. A mass has no direction. A vector here, if it is like this, it represents work. Work has direction. I'm not talking about, this is the work actually, is a number, but if you move an object here to there, the work is opposite when you move it this direction or that direction, right? So this is the direction. That's what I mean by direction, because the vector field, the vector has direction. This one, if we calculate the mass, this f is the density function, so doesn't affect, direction doesn't affect. So if we want to find a mass of an object like this, it doesn't matter if we go from here to there. The mass of a wire like this, it doesn't matter where we go from here to there or there to there. But the vector it is important that we have to specify the direction. So same thing here, we have to specify the direction. So that's the first thing. Second, we talk about the line integral. Now we're talking about surface integral. Just like back in the first few chapters, we talk about equation of a line and equation of a plane. Equation of a line is characterized by a tangent vector. Yeah. So if we write like this, we can say, we can write everything in terms of the tangent vector. That for the line integral. For the scalar version, the vector version of it. So that means both the line integral characterized by the tangent vector. And just like equation of a line, we need the direction vector or the tangent vector. In surface integral, what we need is a normal vector. So in the surface integral, instead of using the tangent vector, we're going to use the normal vector, because the plane is characterized by a normal vector. Remember, talk about this example. It is the equation of a plane, right? So there is that direction normal to the plane. So when I turn the direction of the normal vector, the equation of the plane change as well. Anyway, so now, just like what we talk about the line integral, there are two versions, scalar and the vector form. Same thing here. First we have the scalar version of it, and then we have the vector form of it. So this one is for the scalar. So let f be a continuous function on the smooth surface given by that, right? So it needs again two parameters. Suppose that this is the limit. Let t sub u and t sub v is the derivative of r with respect to u and v respectively. So the reason we use t is because the tangent vector. Think about that. If we have a surface just like this, we have a tangent vector in that direction, the tangent vector in this direction. If we want to find a normal vector, we just do the cross product, and that gives us the third vector, which is the normal vector. So the normal vector is equal to the cross product of t of the tangent vector in the u direction and tangent vector in v direction. And this one we talk about the scalar, meaning direction doesn't matter, or orientation doesn't matter. Because typically when we talk about a plane, there will be two vectors, two normal vectors, one point up and one point down. In the next part of the section, when we do the vector version of it, we have to specify which direction we want the normal vector to point to. But here, this is the scalar version. Direction is irrelevant here. Because apparently, what we do is we find the line integral. I mean the surface integral, because this is the double integral. So as you see, first we write that function in terms of u and v, and then characterized by the normal vector. And the normal vector is the cross product of t. Sorry, that should be the vector t u cross cv, and we're just going to do that in going to be x and y. If we don't have the function here, we calculate just the area of S. Right, so now that we did line integral, this kind of the same step, take the same step. So first, as always, parameterize what we're talking about. Surface integral, meaning we parameterize the surface. Alright, now this is on the cylinder x squared plus y squared equal to 9, meaning that it is on a circle pretty much. A circle, not the interior though, right? So in this case we can say from that x equal to 3 cosine theta, y equal to 3 sine theta, and we're talking about the whole circle, so theta 0 and 3, 2 pi, sorry. And then z, this by itself is another parameter, so if you want to, we just leave it as is. How about just z equal to z, and the z between 0 and 3. Yeah. So usually in the problem, if we see one of something like that, that will be one of your parameters. Don't touch that. So we write parameterize of the surface as follows. It will require two parameters, theta and z. For the first one is 3 cosine theta, 3 sine theta, and then z. And then because that, those are the limits. Right, so we have to parameterize the surface. Next we have to write everything in terms of these parameters. So we have the function equal to y, and y is 3 sine theta. Yeah, so we have y equal, the function equal to that. And next, according to this formula, we need to parameterize the normal vector. So, find normal vector, which is tu, in this case t theta cross t of z. Yeah, just the cross product of two tangent vector. So the tangent vector in the theta direction. So we just take the derivative of this with respect to theta. We have what? Negative 3 sine theta, 3 cosine theta, and derivative of z with respect to theta. There's no theta there, 0. Derivative with respect to z, that will be 0, 0, and 1. So we find the tangent vector. Next, the normal vector is the cross product of t theta cross tv dz. The product of tangent vectors, the cross product of tangent vector. So cross product I, j, k. T respect t theta is that negative 3 sine 3 cosine 0, 0, 0, and 1. Right. So the first component, we cover this, and we have 3 cosine times 1. So for the I component, we have 3 cosine theta I. For the j, that is subtract, and we have negative 3 sine theta j. And then for k, that will be 0. So if we write this as a vector that has three components, 3 cosine theta, 3 sine theta, and then 0. It makes sense because it's just like x and y. So if we talk about a circle, right? The vector field x and y, like for example, if here the point is 1 and 0, right? 1 and 0, so the vector is also 1 and 0. This one 0 and 1, the vector is 0 and 1. This one is negative 1, 0. So pretty much this vector point outside of it. So if we talk about the cylinder, the vector will point on the outside. Right. But it is irrelevant. On this example, we just want the magnitudes of a tangent vector, so we find the magnitude. So the magnitudes of normal vector is the magnitudes of this, equal to square root of 3 cosine square, 3 sine square, and that gives us pretty much x squared plus y squared. So this is r squared, or 9. Right, anyway. So 9 cosine square plus 9 sine square. Cosine square plus sine square is 1, so we take square root of 9, which is 3. Right, so that's what we have. Now we have all the components for the line integral. For the surface integral, for the surface integral, the surface scalar function, and then time ds equal to, now we write the function in terms of the two variables, and then we multiply by the magnitudes of the normal vector, and then dA. dA is certainly is dz and d theta, pretty much two parameters. And theta going from 0 to 2 pi. And z 0 to 3. Right, so in this case we have the integral of 0 to 3, 0 to 2 pi. The function is equal to 3 sine theta. Normal vector is 3. D theta dz. Right, so this is easy enough, right? I group all the z together. And we just have, let's keep the 3 with dz. Of course, you can keep the 3 with theta, it doesn't matter. Or in this case, if we want to, there's the 3 and the 3, those are constant. Why don't we just write outside? And then we just have dz going from 0 to 3, and then 0 to 2 pi. We just have sine of theta. Now we talk about the sine. If we go 1 period, it's going to be 0. So we don't have to do much. Whether sine or cosine, if we go 1 complete period, then that will be equal to 0. So this is 0 times something. This is 0 anyway. Right. So why is this mass equal to 0? If we talk about the mass, right? Density function. By the way, well, this cannot be a mass because density function not supposed to be negative. Remember, we talk about a cylinder. I said this is x-axis, this is y-axis. or if we look at the circle, this upper half y is positive, this lower half y is negative. So because of that, density, some point is positive, some point is negative. They just cancel each other out. So that's why this should be equal to 0. Right, so it's simple enough. Again, parameterize, write a function in terms of the parameters, find the normal vector, in this case the magnitude of normal vector. Right, the calculation of that may be sometimes will get a lot more complicated. And the next one, that's why we have the whole page. Right, derive the surface area of the sphere of radius r. By the way, the reason that will use this r, let's say we don't want to mess with r because the parameters is r, and then r is also the radius. So let's say of radius a. Right. So then we don't have to worry about the repeat of the letter, but a here is a constant. So first, again, parameterize the surface area, and then write the function, and then the normal vector. So this is a surface integral. So first step is parameterize. In this case, we parameterize the sphere. So parameterize the sphere of radius a, which is that. We assume that the radius is at the origin. Otherwise, it's a lot more complicated calculation. But first, we parameterize that. So I think we did this on the first part. Parameterize the sphere. So it's going to be that. But this time we do not have 3. This time we have a. So parameterize like that. Using 2 parameters, phi and theta. We'll have sine. By the way, the radius is a, right? So a sine phi cosine theta for x. A sine phi sine theta for y, and a cosine phi for z. And for the standard sphere, phi from 0 to 2 pi, from 0 to pi, sorry, from the north pole to the south pole. And theta 0 to 2 pi. Right, simple enough. The first step is knowing what is x, what is y, what is z in terms of the parameters x, y, and z. That's good. Next, a function. Since this one we just want the surface area, the function is equal to 1. The density is equal to 1. So this one. Next, find, compute the normal vector. Which is equal to the cross product of using 2 variables here, phi cross t theta. Now there's a reason I leave the whole page here. So first, derivative of r. So the tangent vector in direction of phi. derivative with respect to phi, derivative with respect to sine, derivative of sine is cosine, so you have a cosine, cosine, and a cosine, sine, and derivative of this with respect to phi, negative a sine phi. Next, derivative with respect to theta. Derivative of cosine is negative sine. Derivative of sine is cosine. And derivative of this with respect to theta, there's none because there's no theta there. Alright, next we'll find the normal vector, which is the cross product of these two. You'll say which one cross which one. Is that t theta cross t phi or t phi cross t theta? The answer to that is, in this problem, it doesn't matter because we find the magnitude of it. It will matter if we just find n without the magnitude. But that's not what we have here. Here we just do the cross product. Right, first a cosine, cosine, a cosine, sine, negative a sine, and then we have negative a sine, sine, a sine, cosine, and 0. Right, for the I component, we have, this 0 make a lot of things easier, right? So that, of course, we cover the first row as well. Yeah, so we just have that times 0 and then minus that times that. So for the I component, we have this direction is positive, so that is negative with another negative, so make it positive. So we have a square sine, sine times sine, and then cosine. That in the I direction. Now in the J direction, negative. That again is 0. And then that times that is negative. So it's negative a square sine square and sine theta. That in the J direction. In the K direction, it is a bit complicated, so I will start a new line. So multiply that, a square sine cosine and cosine theta square, and then minus a negative, so that a plus a square sine cosine sine square K component. Right. So if we write that in triangular bracket, we have a square sine square cosine negative negative a square sine sine, and then when you add these two together, you can factor out this cosine square plus sine square is 1. So we just have a square sine cosine. Right, so that's complicated. But if you do a bunch of this problem, you will notice that compare this to the original one, all we did is we multiply a sine phi to it. So just note that. So later on we will use this again. N is equal to a sine phi times r. Yeah, so r is that. We just multiply a sine phi to it. For the sphere, that is. Right, but on this one we want the magnitude, so more work. Magnitude. So those are the components, right? So we have a square sine square cosine, a square sine square sine, and a square sine square. There's no square here. Just sine and cosine. That gives us a to the fourth sine to the fourth cosine square, a to the fourth sine to the fourth phi. This is phi. Sine square, a to the fourth sine square cosine square. Both of them are phi. Now, don't worry. I mean, when we have this, the rest will be very simple. Here cosine square. I mean, I didn't do that earlier, so just have to be consistent here. Both of them have a to the fourth sine, right? So factor it out. Cosine square plus sine square is 1. So we just have a to the fourth sine to the fourth, a to the fourth sine square cosine square. Now we can factor a to the fourth and sine square out. In that case we have sine square left and cosine square. Sine square plus cosine square is 1, so we have 4 a to the 4 sine, and then we just square root of that, so that, and then square root of. You say, why don't I cancel the square and square root? Well, it's not always that case, always the case, right? So in general, we know if we have a square, it is absolute values of a and not equal to a, so they don't cancel out. Absolute values, of course, is equal to itself if a is greater than or equal to 0, and opposite if a is negative. So in this case, this is another thing that we have phi is between 0 to pi. If phi is between 0 to pi, sine of the first and second quadrant is going to be positive. So in that case, sine is positive anyway. So even though we can write a square, square root and square cancel out, give us just that. But this one is positive. After all, the magnitude should be positive or at least 0, right? Yeah. So sine within this, sine is positive. So that's good there. That's good there. Finally, put everything in the surface integral. So here, since we want the surface of ds, we just have 1 times ds because we want the surface. And so the function is equal to 1. So there's nothing there. But we have the magnitudes of n. And then dA. In particular, we have a square sine phi dA. In this case, the two parameters d phi and d theta. Phi is 0 to pi, 0 to 2 pi for theta. Right. Of course, you sure right now you know for sure I'm going to use Fubini theorem, right? We have a square, and then for theta, and for sine phi, so a square, this integral is equal to 2 pi. And what's the integral pi of sine from 0 to pi? So 2. So this is 4 pi a square. So that makes sense. We talk about the surface area of a sphere. So that it is. This is the surface area of the sphere. So this will prove the formula for the surface area of the sphere. So again, it's just like what we did in the line integral. Parameterize, write a function. In the calculation require the normal vector, so we have to find the normal vector. It's not quite simple in this one, but at least we have that. Just note that whenever we do the sphere again, the normal vector is equal to a sine times r. So just multiply that to it, so we don't have to write all of this every single time. And also the magnitude is equal to this, so we don't have to write this every single time. If you remember that, we can just use it. Right, more example. Find the surface area of the cylinder between z equal to that and 16 minus 2x. Now there's slightly a problem here. First, when we look at the problem, look for every clue we know. This is a clue here, meaning that one of the parameters better be theta. Just need to define one more. This is on the cylinder, r is equal to 4. So meaning that pretty standard, x equal to radius is 4, right? So 4 cosine theta. Y is 4 sine theta. And that with that limit. Now we have z between 0 and 12 minus 16 minus 2x. So z, so it is z between 0 and z between 16 minus 2x. 2x is 2 times 4 cosine theta. So I have 16 minus a cosine theta. Right. And remember, this is z. This is not z equal to that. We're talking about the surface. If we have to sketch, I will sketch. We have a cylinder. try to be a little more precise, a little less sloppy. So we talk about the cylinder X, Z, Y, like that. Talk about cylinder. And then Z equal to 16 minus 2x, so it looks like this. So that is a plane. This is the plane. So what it actually look like? So look like that we have a cylinder and then we have a plane that is cut it in an angle like this. So a top is that, the bottom is this. So we just like we have a tube and we slide not a tube. Oh, yes, it is a tube. So I have a tube and then we cut it just like where we have a straw and then we cut it, but not cut it perpendicular to the straw. We cut it at an angle to the straw, and that's what we have here. Right, so the limit is slightly different, but in this case, notice Z varies from here to there, so Z has to be a parameter. I repeat, Z going from 0 to that value, so Z has to be a parameter. So in this case, this is what we want to write. So the first step is always parameterize the surface. R will depend on two variables, theta and Z, two parameters. We have X is 4 cosine, Y is 4 sine, and Z is Z. Now the limit is a bit tricky though. Z go from 0 to that, so we have to write limit Z between 0 and 16 minus a cosine theta and theta 0 to 2 pi. That's what we know. So that is the parameterization. It's not as bad. Next, this one we want to find the surface area. So for surface area, our function equal to 1. So every time we find the surface area, we just take 1. So that's equal to 1. Right. Next we find the normal vector, magnitude of it into direction of theta cross Z. Right, so derivative with respect to theta, negative 4 sine theta, 4 cosine theta, and Z has no theta, so that will be 0. Derivative with respect to Z, no theta here, no theta here, no Z on the first two, and Z is equal to 1. Now let's do the cross product. Negative 4 sine theta, 4 cosine theta, and 0, 0, 0, 1. This is very simple. For I, there will be 4 cosine theta, J -4 sine theta K 0 minus 0. So we just have 4 cosine theta, 4 sine theta, and then 0. So this is the normal vector, which of course pointing out, but we're not worried about direction here. We just need the magnitude. So 4 cosine square, 4 sine square, so we have 16 cosine square plus 16 sine square. Cosine square plus sine square is 1, so square root of 16 equal to 4. So we have all the components for the surface integral. This time we want to find the area of S. Or we just have 1 here. And we have 1. So then we have the normal vector times dA. Now to slide it different here on the limit though. By the way, normal vector is 4. dA is d theta dz. Oh, it's not dz, d theta. Let's take a look. Z is between, oh, this is not between two constants. So this is not d theta dz. It has to be dz d theta. Because when we have the limits like that, whatever constant must be on the outside. And then dz go from 0 to 16 minus 8 cosine theta. Right? So this is not for linear theorem because we don't have the constant limit. So we have 4z go from 0 16 minus 8 cosine theta d theta. 0 to 2 pi. Put this in for z, we have something. Put 0 in that, we have nothing. So 4 16 minus 8 cosine theta d theta. So we have 0 to 2 pi. I will multiply out 64 minus 8 cosine theta. Right. I will split the integral. Yeah, you can take the 8 outside if you want to. But once again, I did mention that when we have sine or cosine, and when it goes from one period or two period, it doesn't matter. If it is a multiple of period for sine or cosine here, that part automatically equal to 0. Of course, we can always do that. There. So I have 64, and the integral here just 64 theta 0 to 2 pi. Put in 2 pi, put in 0, we have 128 pi. So that is the surface area of that object, which is a tube. I mean, this is just like a straw, but we cut it. So just like a straw. and on the surface, yeah, this straw wood we just cut it diagonally, right? So that's nice and all. Next, for a special case, let f be a continuous function on the smooth surface S given by z equal to g of xy. Now we have z depends on x and y. For x, y in a region R, the surface integral of f over S is given by that. When f of x, y, z equal to 1, the surface integral equal to the surface area of the surface. Right. So the only thing different here is that we have that thing. So what's that equal to? Right. So we're going to prove that quickly. Actually, this is very easy to prove. Right. So as always, parameterize the surface. So this time we parameterize using two parameters, x and y. And we have x is x, y is y, z is the function of x and y. And in this case, we just have x, y in the region R. Right. Of course, the function in terms of x, y, z, so that there's nothing new here. So the function of x, y, z is the same as the function of x, y, and z is the function of x and y. Next, the normal vector. Cross product with respect to x, with respect to z. Of course, then we will find the normal vector. Right. Now, derivative with respect to x. In this case, 1, 0. Derivative with respect to x, we just write g sub x. Or if we want to, z sub x. Z equal to g of xy. And t of y, 0, 1, z of y. Now the cross product. Right. 1, 0, z sub x. 0, 1, z sub y. And this will be simple enough. With respect to I, that will be 0 and negative z sub x. With respect to I, negative z of y. And with respect to k, that will be 1. So if we want the normal vector, the magnitude of it, just square root of the square of those components. So that's why in here, that is just a normal vector. That makes sense. Right. So in that case, finally, we can write the surface integral equal to the function in terms of xy and the function of xy. The normal vector is that. And then the x dy, dy dx, let's just write the a over the region R. And so that's exactly what we have. And the proof is fairly simple. Right. So next we have this example. A thin conical sheet is described by that. And z is equal to 0 to 4. All right. Usually when we see that this is a goal, one of parameter should be z. But on this one, yeah, we can choose use z. Why not? But think about this. We talk about the cone, and obviously this we have the hint. R is the whole disk here. So in that case, we can let x equal to r cosine, y r sine, r go from 0 to 4. And by the way, this is r, so z equal to r, the surface. So that's very convenient. Right, so the first step is, of course, by the way, we just set up the problem. I'm not sure if we can evaluate this, but at least set it up. So first, parameterize the surface. So if that disk x equal to r cosine theta, y equal to r sine theta, and z equal to x squared plus y squared. So in this x squared plus y squared, with this condition, we just say it to the 1/2. So r cosine square plus r sine square. The square is on the outside. One-half. So that gives us r squared to 1/2, so just r. So conveniently, the parameterized surface given by two variables r and theta. Sorry, it is bad. So usually they might refer this to a different variable, but as long as we write differently, it's fine. Right, r cosine, r sine, and r. Right, so that's good. Limits. For that disk, r 0 to 4, and theta 0 to 2 pi. So that's good. Next, the function, the density function. And z equal to r, so this is just a minus r. Right, now we put everything into the surface integral. Now we write f as two parameter and then we can find the normal vector. You said, why didn't we calculate the normal vector? Well, we didn't have to, because if the equation given then this, we're just going to use that for the normal vector. The A is just write the A for now. By the way, we haven't done the z sub x and z sub y, which is if it is in that case, what's this? Z sub x and then z sub y. Yeah, still need to calculate that. Yeah. So this is we know z is equal to r. Actually, this is much better. Just calculate the normal vector. Okay, we do both. I'm just going to calculate this vector here. So that is derivative with respect to x is going to be 1/2. Take that to 1/2 x squared plus y squared to the negative 1/2 times 2x. So that is the derivative with respect to x. And with respect to y will be similar. One, 2 and the 2 cancel out, so we just have x squared over x squared plus y squared. Of course, we have this. You just write this to the 1/2, move to the bottom, and x on the top. Yeah, so let's write like that. Again, 2 and 2 cancel out. We have y over x squared plus y squared to the 1/2 square. So I have x squared plus y squared, y squared, x squared plus y squared. I combine the two later fraction. We have 1 plus x squared plus y squared, x squared plus y squared. So this gives us square root of 2. Right, so like I said, one way to do that. Now the other way to do that is where we look at this and we take the derivative with respect to r. With respect to r, not the bone face r. That's one way to do that. The other way to do that is take derivative with respect to r. Give us cosine, sine, and 0 and 1, sorry. And then with respect to theta, negative r sine, negative cosine, r cosine, and 0. Do the cross product. cosine sine 1 negative r sine r cosine and 0. So cross product, the first one give us negative r cosine and wait, yes, negative and r sine, actually that also negative, and then that just be r cosine square plus r sine square, so it's r. So then what we have is the normal vector is equal to what? Negative r cosine r sine and r, both negative, and the magnitude r cosine square plus r sine square plus r square. So bottom line is cosine square plus sine square is 1, so we have r square plus r square, so we have 2r square, so we have square root of 2r. Well, what did we miss? What did we miss? And what the answer should be? Think about that. Right. Now let's just write this down. If we're going to write like this, everything is, oh, I make a mistake here. This will be in terms of x and y. Correct? Because everything's supposed to be in terms of x, y. So this should be square root of 2. So let me write this one more time, then you'll see why in a minute. Yeah. So in this case we have s f ds. The function is a minus z and z is that. So we have a minus x squared plus y squared. And then square root of x, that is square root of 2 dA. And this is the limit. I'm just going to draw the disk of xy. If in terms of xy, that's what we have. However, what we actually write, remember, now if we convert everything to r and theta, so this 8 minus r x squared plus y squared to 1/2 is r, and then the square root of 2. And what did we say about dA in polar? R dr d theta, and then the theta go from 0 to 2 pi, r go from 0 to 4. So it's not that bad. We just need to integrate this. Very simple though. I just want to emphasize that if we write everything in terms of x, y, in this calculation, they're missing an r, and rightfully so. If we convert to polar, then the r will automatically appear. So if we write everything here in terms of that parameterization, then we're going to end up with r and theta with this. By the way, in this, because of that, this problem we do not parameterize the surface using r and theta. If we want to use that formula, we just say the surface is x and y as x, y, and the function. Yeah. So remember, in that formula, we can only do that the variables x and y. So if we want to keep the x and y, that is our parameterization. In that case, that worked out just fine. But if we want to convert to r and theta, by all means, this is a lot easier to do, which turn out to be the same. Right. So whether we just do the surface integral and we want to keep x and y, in that case keep x and y, we end up with this. Or if we want to parameterize that using r and theta, just do that, and that would take care of the Jacobian nicely as well. So remember, if you want to parameterize using x and y, just use that. But in this case, that calculation is complicated. If you want to use r and theta, the normal vector kind of complicated also, but we have an r there, which will go with dr d theta, make a dA. So that perfectly, it makes perfect sense there. Right. So next we will have the vector field for, the surface integral for the vector field. So this is the vector version of it. And as mentioned before, if we're talking about line integral or surface integral, we should worry about the direction. Because for the surface, there are normal vector pointing up, normal vector pointing down. We have to specify that. And once we specify, the calculation is still very simple. Just that. So instead of use the normal vector, we're just going to write, instead of use the magnitude, we just write the normal vector and then dot product with the vector field. So that's the whole thing different there. So the vector field in terms of the parameters, then dot with the normal vector. Right. So pretty standard here. So first, parameterize the surface. So parameterize the surface S. So the surface S is bounded by this one, which is the plane, but this plane is only on the first quadrant, the first octant. And when we let z equal to 0, this equation is 4 minus 2x minus y equal to 0. So we write y equal to 4 minus 2x or minus 2x plus 4. Meaning if we have the table of x and y, when x equal to 0, y equal to 4, and when y equal to 0, x equal to 2. So on the x-axis there 2, and then on the y-axis there's 4. At least we have that. Now this is the plane, so very simple. We just say z is equal to 4 minus 2x minus y. That is the plane. So if we parameterize using x and y, it will follow x, y, 4 minus 2x minus y. And then difficult to write the limit, so we just say x, y, and I'm going to draw it instead. 2 on the x and 4 on the y. Right, nice enough, right? Okay, the vector field. The vector field we have to write is 0, 0 and -1. In this case, we're just going to keep it because we don't have to write in terms of x and y because there's no x, y in there, so that's perfectly fine there. Next, we write the normal vector as a cross product of tx cross ty. Derivative of this with respect to x, 1, 0, -2. And derivative of this with respect to y, 0, 1, -1. Right. So in the I component, that's 0, negative. I don't know why I wrote the line there, sorry. In the I component, that's 0, -2, so that will be 2. For j, -1, -1. And for k, that will be 0. So in that case, the normal vector is 2, 1. Sorry, the last one is not 0, it is 1, right? Right. So this is good and all. But there's a big important thing here. Find the flux in the downward direction. This is -z. Here we have a positive z, so it's not right. Remember, this is the downward flux. With z less than 0. So usually if that is the case, we just cross, instead of tx cross ty, we do ty cross tx, but we don't even need to do that. So the normal vector equal to, we just turn that to opposite direction. Because after all, remember, we want the z to be negative. So for the surface integral in the vector form, always read the question and determine, do we need to keep the normal vector or we do want to reverse it? That is very important. In this case, we need to reverse it because the problem says z is negative, so we have to turn that to negative. Right, so we have the normal vector. Right, and now get back to the formula for the surface integral. And by the way, the reason we know this is in the vector form because we write like this. Line the line integral, right? But now we write the vector field in terms of the two parameters, x and y, dot the normal vector times ds, or just or t, or the cross here, or just dA if you will. Yeah. So if they are equivalent, then the dA is just ds here, pretty much. So make sure that the n normal vector here have to be in terms of x, y. In this case, all of them are constant, right? So in this case, the reason there's a difference here, because if we write in this n, this is in original in x and y. So this is in x, y. This is in uv. In this example, we did say the two parameters x, y. So So that's why ds is equal to dA. Yeah, because they just xy also, so that's why ds is equal to dA. Now the vector field in terms of xy, in terms of the parameter dot product, the normal vector -2, -1, and -1, and dA, because in this case they just xy, so we can just write dA, which is this triangle. Right, let's just do the dot product. 0 plus 0 plus 1. So dot product gives us 1. So what do we have here? So in that case, give us 0 plus 0 plus 1. What we have is just the area of a triangle. 2 by the base is 2, the height is 4. So 1/2 base times height. Right. So notice in this formula, if both of them in terms of xy, then ds is equal to dA. We don't have to worry about the variable changing. If it's not, then we have to do the cross product and then determine. Most importantly, I said the step will be similar, but most importantly, in this case we will use the vector form of the normal vector, and the vector form of the normal vector make sure that point in the same direction as we want to. Right. One more example. Find the surface integral where S is the surface of the cylinder. So xy plus y squared equal to 4 between z. Okay. So we have a cylinder. Right. If it is a cylinder, the normal vector may be pointing outside or maybe pointing inside. But in this case, it's not specified. But let's assume that, suppose we do that, let's say the normal vector pointing outside. So by default, usually the normal vector pointing outside. So in this problem, I forgot to specify, but let's say find the surface integral with that. Assume, so find a surface integral with and point outward. Outside of the cylinder. And this is the vector field. Right, so the first thing as always, for most of the problem here, we parameterize the surface. Right, if it is like that, we know z between 0 and 3, so that one is gone. One parameter is 0 to 3. The other parameter will come from the cylinder itself. Xy plus y squared equal to 4. So if x equal to 2 cosine, y equal to 2 sine, and then z, theta 0 to 2 pi. Right. Next, the vector field. Negative x, y, and tangent of z. In terms of these parameters, negative 2 cosine, 2 sine, and z is still z. Sorry, I should have write the parameter theta and z, 2 cosine, 2 sine, and z. Yeah, sorry. And we use this parameter. So x, negative x, y, tangent z. So it's good. So we have parameterized it, the vector field or function, in this case the vector field in terms of x, y, z, those parameters. Next, the normal vector is derivative with respect to two parameters, theta cross respect to z. Notice that if we do this, and then when we write the formula, and we don't have to worry about is that in 8 or when we get there, we specify one more time. But first, derivative of this with respect to theta. I think we did plenty of this. Negative 2 sine theta, 2 cosine theta. There's no theta there. With respect to z, 0, 0, and 1. Right, normal vector. Cross product I, j, k, negative 2 sine, 2 cosine, 0, 0, 0, 1. Right. So first one, 2 cosine theta, negative 2 sine theta, and 0. Yeah, that's easy. Right. Note that in this problem, we want the normal vector pointing outside, right? So it is true. For that, it's very simple. We have the circle x squared plus y squared equal to 4, right? Let's say at theta equal to 0, the normal vector equal to what? Cosine of 0, 2 sine of 0, and 0. Cosine of 0 is 1, sine of 0 is 0. So ignore the z. X and y, we have 2 and 0, so vector pointing outside. So this was point outward, so yes. That means we do not need to reverse this. Usually we just need to check one point. If it happens to be point inside, we have to reverse it and make it point outside. In this case, we don't have to. Finally, let me be more precise in the notation. So we can write like that. Now if we write the vector field in terms of the parameters, in this case theta and z, and then dot the normal vector, which is fine, but the normal vector in terms of theta and z, and then we just have d theta and dz. So don't have, there's no r d theta, so there's nothing like that here. Like I said, if we write everything in terms of theta and z, in terms of the parameters. Everything in terms of parameters for the normal vector. In that case, that's just the limit there. The limits for theta 0 to 2 pi, and the limit for z 0 to 3. Yeah. So if we write like that, this will be fine. By the way, does that make sense? Remember, we have this for line integral. Then we say if we can write the vector field in terms of t, and then dot the tangent vector in terms of t dt. So what's the difference here, right? This one has two parameters, so the vector field has two parameters. Line integral characterized by the tangent vector, surface integral characterized by the normal vector in two parameters. Yeah. So, write. Another way to write this is, of course, you can also write S F dot and ds, which is equal to that as well. So make sure when we write everything in terms of the parameters, that will be very clear. The vector field and the normal vector, both of them have to be in terms of the parameters. Right, so 0, 3, 0, 2 pi. Right. The vector field, negative 2 cosine theta, 2 sine theta, tangent of z. The normal vector will be that 2 cosine, 2 sine, 0, and then d theta, dz. Right. The dot product gives us negative 2, so negative cosine square, negative 2. Cosine square plus 4 plus 4 sine square d rho dz, d theta dz. Of course, there's no z here, so we just need to do that integral. I got a feeling that it is equal to 0. Because cosine square minus sine square is cosine of 2 theta. And cosine of 2 theta, the period, is a theta. Yes, it is equal to 0. So for Bini theorem, I group the z, I group cosine square minus sine square is cosine of 2 theta, but this case, so this is equal to negative 4 cosine 2 theta, negative 4 cosine 2 theta, and so that integral of negative 4 cosine 2 theta go from 0 to 2 pi. the period of this one is 2 pi divided by 2, so the period of this is a pi, and this one have 2 periods, so that will be equal to 0. Like I said, integral of sine, cosine, if we have the multiple of periods, that will equal to 0. Exactly what we have here. So bottom line is, to be more precise with the notation, if we can write the vector field in terms of the parameters and the normal vector in terms of the parameters, then we just evaluate everything in that parameters. Right. So once again, that's surface integral. There's two versions, the vector field and the scalar version of it. All of them, the first part almost identical, parameterized. If we have the vector field, we write that in terms of the parameters. If we have the function, write that in terms of the parameters. And then compute the normal vector. Both of them have to do that. In the scalar version, we're going to take the magnitude of it. In the vector version, we do not take the magnitude, but always have to check with the condition. If the vector field that's pointing outside or start pointing inside, that is very important. If it is pointing the opposite direction as we want to, just turn to opposite and then just do the calculation. Bottom line is, let me clear the formulas. So if we write like this, it is fine. I mean, that end, so this is in sy, that's why this is still s. S is the region of x and y. So a way to rewrite this, we can say, if there's a way we can write the vector field in terms of the parameter u and v, and then this is the normal vector. I should specify this is the normal vector in terms of u and v. That will be clear, right? That dot product with the normal vector of u and v, and then dA. So either form here should be fine. So that's very consistent with the line integral. Write the vector field in terms of the parameters. Write the vector in terms of the parameters. In the line integral, that vector is the tangent vector. In the surface and the surface integral, that vector is the normal vector. So there's no difference here. Here we use the normal vector characterization of a surface. Here we use the tangent vector characterization of a line or of a curve. Right. So everything in terms of that parameters, limit of the parameters, and that should be fine. Just like this. If we want to keep the s, if we use x and y, that's going to be dA or going to be ds. If we want to write in terms of the parameters, that will be different. So make sure that if I recommend we write in terms of the parameters and then just do the cross product and find the normal vector that way. Anyway, with that, I stop this section right here. As always, thank you for watching.